Hello everyone, this is Sir Brian Orlason Cordova. Welcome to my channel. So our topic for today is limits of function. So for definition, we have the limit of the function f is the number L which the value of the function f of x approaches as the value of x approaches to a number c. So in symbol, we have limit of f of x as x approaches c is equal to the value L. So in graph, given the graph of the function y is equal to f of x, any point on the graph has a coordinate x f of x. And if the value of the x coordinate is equal to a, the coordinate of the point is a f of a, which is our y coordinate is equal to f of a, which is the function value where our input is a. And if that point approaches another point, so the value of the input also approaches a certain value. For example, c, the new coordinate of that point would be c f of c. And the y coordinate is f of c, which is the value L that we are going to approach as x approaches c. The first function that we are going to find a limit would be the identity function f of x is equal to x. That is the graph of the function y is equal to x, where the input is equal to the output. So given a point on the graph, if its x coordinate is 3, then to find the limit of the function f of x as x approaches 3, since the value of f of x is equal to x, we can change that into this form. And since y is equal to x, the y coordinate would be the same. So the coordinate of the point is 3, 3. So the value of y, which is equal to the limit, is also 3. In general, the limit of x as x approaches any value, c, is just equal to c itself. Another function that we will use, the constant function f of x is equal to k. Constant function is represented by a horizontal line where k is the value of the y-axis where this horizontal line intersects. So for example, if the function is equal to y is equal to a constant 4, then in any part of the graph, our value for y is constantly 4. So if we're going to find the limit of the function as x approaches 2, it is still equal to 4. Or if we find the limit of the function as x approaches 8, it is still equal to 4. So find the limit of 4 as x approaches any value c, it is still equal to the constant value 4. In general, the limit of k, which is the function as x approaches any value c, is equal to k itself. There are also non-existing limits. For example, function u of x is equal to 0 if our x is less than 0 or the values of x are negative, and is equal to 1 if x is greater than or equal to 0 or 0 or positive x. So in graph, we have this one. So the input is negative values and the y coordinate is just equal to 0. And if positive and 0, the value of the function is equal to 1. And it has no limits as x approaches 0 because the values jumps at x is equal to 0. So as x approaches 0, its value becomes 1. Okay, and from the right, as x approaches 0 from the right, so the value is equal to 1. There is no single value L approached by the function u of x as x approaches 0, since we have two values that is being approached, which is 0 and 1. Thus, the limit of the function u of x as x approaches 0 does not exist. Another non-existing limits, for example, given a function g of x is equal to 1 over x, So if we graph this function, we have a symmetric to the origin. Okay, y is equal to 1 over x. So g of x has no limit also as x approaches 0, because the value of g grows too large in absolute value as x approaches 0, and do not stay close to any fixed real value, because as x approaches 0 from the left, the value of the function approaches negative infinity. Okay, and as x approaches 0 from the right, the value of the function approaches positive infinity. And since it does not stay close to any fixed real value, we say the function is not bounded. It goes to both negative and positive infinity. Thus, the limit of g of x as x approaches 0 does not exist also. Another one is given by the function is equal to sine 1 over x. So it is a trigonometric function. Okay, so this is its graph. So we can see that the function has no limit also as x approaches 0. Why? Because the function's value oscillates too much to have a limit between positive and negative 1 in an open interval containing 0. So as x approaches 0 from both sides, so the function oscillates endlessly. Thus, the limit of the function as x approaches 0 also does not exist. Now we have theorems on limits. First is the basic limit laws. Number 1, constant multiple rule. If the limit of the function f of x as x approaches c is equal to m, then the limit of k times the function of x as x approaches c is equal to k multiplied by the limit of the function f of x as x approaches c, or it is equal to k times m, where k is a constant. So we can see that k is a constant multiple of the function. So if we can find a constant multiple of the function, we can factor that out to find a limit of much simpler function, and later multiply the constant multiple. Example, find the limit of the function 4x as x approaches 2. So if we can graph this function, that is y is equal to 4x, our solution would be change the given following the constant multiple rule. So we factor out 4 and we will multiply it to the limit of the remaining function, which is the identity function f of x is equal to x as x approaches 2. So we can use the previously shown solution for identity function as x approaches 2. We can recall that y is equal to 4x is just equal to y is equal to x, only stretched away from the x-axis by a factor of 4. Or it is being compressed to the y-axis by also a factor of 4. And we know that the limit of x as x approaches c is equal to c. So as x approaches 2, the limit of x as x approaches 2 is equal to 2 also. Hence, the limit of 4x as x approaches 2 is equal to 4 times the limit of x, which is 4 times 2, which is equal to 8. Number 2 is sum and difference rule. If the limit of f of x is equal to m as x approaches c, and the limit of the second function g of x as x approaches c is equal to n, and again the limit of the sum or difference of two functions as x approaches c is equal to getting the sum or difference of the limits of these functions. Example, find the limit of 4x minus 2 as x approaches 3. So we can graph this function y is equal to 4x minus 2. So we are going to find its limit as x approaches 3. Solution, So we can change this by following this difference rule. We have limit of 4x as x approaches 3 minus the limit of 2 as x approaches 3. So this is actually two functions. We have y is equal to 4x and y is equal to 2. So we're going to get the difference between these two functions and get their limit. So we know that first limit have a constant multiple 4, and we have the identity function limit of x as x approaches 3 minus the limit of 2, which is constant function. Since we have the limit of x as x approaches 3 is 3 and the limit of 2 is equal to 2, we have the limit of 4x as x approaches 3 is 12 and the limit of 2 as x approaches 3 is 2. So 12 minus 2 is equal to 10, and that is the limit of the original function 4x minus 2 as x approaches 3. Number 3, product rule. Given the same argument, given the limit of two functions, f of x and g of x, which is m and n, as x approaches c. So the limit of the product of two functions as x approaches c is equal to the product of their limits. Example, find the limit of x squared minus 1 as x approaches 3. We can graph the function y is equal to x squared moved downward by 1 unit, so minus 1. And we were going to find the limit as x approaches 3. Solution. Since the given function has factors x minus 1 and x plus 1, so it is a product of two functions. So we can take the limit of those two factors, y is equal to x minus 1 and y is equal to x plus 1 as x approaches 3. So we can multiply their limits later. In each factor, we can use sum and difference rule. That is limit of x minus the limit of 1 as x approaches 3 times the limit of x plus the limit of 1 as x approaches 3. Since each of the terms are either an identity function or a constant function, can easily find its limits. So the limit of x as x approaches 3 is 3 minus the limit of 1 as x approaches any value is still 1. And again, same with the second factor, but in addition. So 3 minus 1 is 2, which is the limit of x minus 1. And 3 plus 1 is 4, which is the limit of x plus 1 as x approaches 3. We have 2 times 4, which is equal to 8, which is the limit of the original function x squared minus 1. Number 3, quotient rule. So finding the limit of the quotient of two functions f of x over g of x as x approaches c is equal to the quotient of the limits of these two functions. Example, find the limit of 2 over x plus 2 as x approaches 2. The function is equal to a hyperbola symmetric to a certain point. Getting just part of the function y is equal to 2 over x plus 2 close to the origin and x is equal to 2, we have this one. And we were going to find the limit as x approaches 2. The solution. So following the quotient rule, this is equal to the limit of the numerator over the limit of the denominator. The numerator is actually a constant function, y is equal to 2, and the denominator is a linear function, y is equal to x plus 2. So using the sum rule on the denominator, we have this, and taking the limit of the constant function 2 as x approaches 2 is equal to 2, and the limit of the identity function x as x approaches 2 is equal to 2 also, plus limit of constant 2 is equal to 2. So the limit of the denominator is equal to 4. So we have 2 over 4, which is equal to 1/2. Therefore, the limit of the function y is equal to 2 over x plus 2 is equal to 1/2. Number 4. Our rule. Given the limit of the function, which is equal to m, limit of the nth power of the function as x approaches c is equal to the nth power of the limit of the function. Example, find limit of x minus 1 quantity squared as x approaches 0. We can show this as the parabola opening upward, where the equation of the parabola is equal to y is equal to x squared minus 2x plus 1, or equal to x minus 1 quantity squared. We're going to find the limit as x approaches 0. Solution using the power rule, and change this into a power of the limit of the function. Okay, so we can now evaluate the limit of the function inside the power, which is the function y is equal to x plus minus 1. Using also the difference rule again, so it's the limit of the identity function as x approaches 0 minus the limit of the constant function 1 as x approaches 0. Since their limit is equal to 0 and 1, so 0 minus 1, we have the limit of the function as x approaches 0, which is equal to negative 1. Squaring negative 1, we have positive 1. So that is the limit of the function y is equal to x minus 1 quantity squared. Number 5, root rule. So given the limit of the function f of x is equal to m, so the limit of the nth root of a function as x approaches c is equal to the nth root of the limit of the function as x approaches c, provided that it is a real number and the index of the root is a positive integer. Example, find the limit of the cube root of x plus 1 as x approaches negative 9. We can graph this like this. So y is equal to cube root of x plus 1. So it is the graph of y is equal to cube root of x shifted to the left by 1 unit. So we will find the limit of the function as x approaches negative 9. Solution. So we can put the root outside the limit. So x plus 1 is actually a linear function y is equal to x plus 1. And using the thumb rule, we have cube root of the limit of x as x approaches negative 9 plus the limit of 1 as x approaches negative 9. Again, this is identity function and this one is a constant function. So the limit of x as x approaches to negative 9 is negative 9, and the limit of the constant 1 as x approaches negative 9 is still 1. So we have cube root of negative 8, meaning the limit of the inner function, which is x plus 1, is negative 8, and we can take its cube root, which is equal to negative 2. Okay, number 6, the limits of a polynomial function. Given a polynomial function p of x, which is equal to a sub n x raised to n plus a sub n minus 1 x raised to n minus 1 plus so on and so forth up to plus n sub 0, then the limit of the polynomial function as x approaches c is equal to the function value where x is equal to c. So we are going to substitute the value of c into the variables x and evaluate, and we will get the limit. Example, the limit of x cubed plus 4x as x approaches 3. So substituting the value of 3 to the variables x, we have 3 cubed plus 4 times 3, which is 27 plus 12, and we have 39. Number 7, limits of a rational function. If p of x and q of x are polynomials and q of c is not equal to 0, then limit of the quotient or the rational function p of x over q of x as x approaches c is equal to the polynomial function values of p of c over q of c. Example. So finding the limit of x squared plus 2x minus 5 over x plus 2 as x approaches 2. Substituting 2 to the variables x from both numerator and denominator, we have 2 squared plus 2 times 2 minus 5 over 2 plus 2. Since the denominator, which is q of c, is not equal to 0, we have 4 plus 4 minus 5 over 2 plus 2, which is 3/4. In summary, given that if the limit of a function f of x is equal to m as x approaches c, and the limit of g of x is equal to n as x approaches c also, then we have the following rules. Constant multiple rule. Limit of the product of a constant times a function is equal to constant times the limit of the function, okay, where k is a constant. Sum and difference rule. We have the limit of the sum or difference is equal to the sum or difference of the limits. Product rule. The limit of the product is equal to the product of the limits. Quotient rule. The limit of the quotient is equal to the quotient of the limits. Power rule is the limit of the power is equal to the power of the limits. The power is a positive integer. Root rule. The limit of the nth root of the function is equal to the nth root of the limit of the function, provided that it is a real number and n is positive integer. Limits of polynomial functions. If p of x is equal to this expression, then the limit of this polynomial function as x approaches c is equal to the function value p of c, where we substitute c for the variables x. And limits of the rational functions. If we have the quotient of two polynomials and the function value of the denominator is not equal to 0, then we can take the limit of the quotient is equal to the quotient of function values p of c over q of c. And that's all.